All right, let's get started.
Morning. Morning. All right, so I was gonna do that. I will take a couple more questions on this quiz, and then just a couple things. As you are working on stuff, and perhaps this quiz, I'm gonna let you use a single-sided 8.5 by 11 cheat sheet for the next exam. And then use that same cheat sheet, flip it over, and use the other side for the final exam. So then you don't have to duplicate the last two chapters, right? So essentially you would go back and add, the first ones. Okay, does that make sense? So 8.5 by 11. For the next exam, I don't know if I would have. And you can have some formulas like this that are up there, and I don't have to put them in the question and stuff like that. It kind of makes sense. Then the other thing, I'm very happy where we're at schedule-wise. I think we're rushing at the end. I think we're good. But as we start doing Lewis structures, which we will do today, you want to start poking around to see what you can do for OWL for the last. I have all the data. The one monstrous one towards the end, I think the average completion time is over 3 hours. But I think some of it's just figuring out how to put the electrons in and stuff. I think some of it's just you got to figure out how to. It gets a little nitpicky because we're going to be doing Lewis structures and putting the electrons in. So maybe that data is not great, but. It does end up being, I believe, the student average is well, I know it's the longest throughout the semester, is one coming up. You might poke around in there. I know you're gonna have other exams and stuff like that, so you can always poke ahead, right? In the OWL, they should be open. You can poke ahead and look at them. So, okay. Let's see. Do you have anything on this quiz that's due Sunday then? Yes.
Number
10. Let's see. 10. I think I'm sharing the screen. This should be recorded. So 10. Let's look at 10. Let me see this. So if we wrote this out. This is our 7 levels. And we know that this is S2. We can put 2 electrons there. Then we start here at P, and we know this would be P6. And then we go D, and we know this would be D10. And then F, and we know that would be F14. Now, if we added up the electrons for each level, the maximum electrons here would be 2, right? Just S2 in level 1. Then in level 2, we can go 2 here, 6 here would be 8. Level 3, we can go 2, 6, and 10. This would be 18, correct? Now, let me show you that max electrons is given by 2n squared. So if I put a 1 in here and square it, obviously we get 1. 1 times 2 is. There's my 2, right? If I put a 2 in here, we're going to have 2 squared for 4 times 2. There's my 8. If I put a 3 in there, I'm going to get 3 squared is 9 times 2 is 18. If I put a 4 in there, 16 to 32, right? 32. Now, does that work? Absolutely it does, because we would just add 14 onto this. Now, the problem is, in order to get level 5, there is a G, I believe, goes H. You could go farther. You'd have to go farther with this. But let's just put a 5 in. What do we get if we put a 5 in? 50. We get 50, right? So that is the answer. You could actually, there are some more letters that they add. And then as we go up, now this is 1 orbital, 3 orbital, 5 orbitals, 7 orbitals. As we go up by odd numbers, the next one would have 9 for 18 electrons. If we add 18 onto the 32, we would get our 50, right? The number of orbitals goes up by odd numbers. So if we are continuing on, the next one have 11, right? And that's beyond what I even want to talk about. We even want to talk about. Okay, what else do we have on this quiz? This will be your last opportunity. Yes.
19.
19. Let's look at 19, 19, 19. Okay, 19. All right, all of the elements in group 1. So the elements we're talking about in group 1, hydrogen, and then lithium, sodium, potassium, rubidium, cesium, francium. All of them, we'll talk about this of why hydrogen is a -1 for hydride, but +1, +1, +1, +1, +1, +1. In order to have +1 charge, it has to, we gotta lose an electron, right? Now, remember, it's all about, we're not doing this stuff. We are never, ever changing protons. If you change protons, you are changing the element, right? So, all of these need to lose a single electron to become a positive ion. If it gains the electron, it would be negative. But we all got to lose an electron to become a positive ion. Anything else on the quiz? Yes. 2, 0. An element that has 2 valence electrons. Okay, this is perfect for today as well, because we are going to talk about this and we're going to add this to the periodic table. In fact, I don't think I added that to the blank periodic table now, did I? I'm going to do that right now because this is exactly what we're going to talk about today. So I'm going to get this. I'm going to go to the blank periodic table. So get to your blank periodic table. Do this. Okay. So this is our blank periodic table. And how many valence electrons for the elements in group 1? How many valence electrons for everything in group 1? And the answer to that is 1, right? Because let's just take sodium here, 2p6. After 2p6, remember, valence electrons, highest level S or NPs if it's the same number. As soon as we go to 2p6, 3s1, this is 1 valence electron, right? We're not gonna count anything less than 3. Those are the core electrons. So every time we are writing here, all of these have 1 valence electron because every time we start a new row, we start a new level farther up. So everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. And in fact, on our fancy electron configuration notation, it actually has it right here. because we're not going to include any of these electrons here that are the same configuration as neon. So there's our one valence electron. We're not going to include these core electrons here of argon, one valence electron, and everything here has two valence electrons. Now, as we get into the middle, I want to shy away from this. Some textbooks will say, well, they're going to include unfilled Ds. Some are just going to try to wade through. I'm just going to try to stay away from that in the middle, okay? But as we get over here, aluminum. How many valence electrons for aluminum? 3 from the 3s2, 3p1, right? 3. How many for gallium? 3. How many for indium? 3, and so on. If we go to, and this I'm going to say is group 13. If we go to group 14, how many valence electrons for carbon? 4, silicon, 4, and so on. If we go to group 15, how many valence electrons? 5. What is the pattern? The number of valence electrons equals the ones place in that column or group. So that's what I want to add to this periodic table. This is, we're going to do this. I'm going to say this, I don't know how many times now for what's coming up. So group 1 and 2, we know that that group number equals our valence electrons, right? So we know everything in group 1 has 1 valence electron. It loses that valence electron to become a +1 ion. And then you have the noble gas configuration. Everything in group 2 has 2 valence electrons. Everything in group 13 has 3, 14, 4. So it becomes the ones place here. Now, except for helium here. Helium has 2, but everything else down below it has 8, right? 8. So the number of valence electrons is equal to the ones place here. Okay, so now finally back to my question, but this leads in perfectly with what we're going to talk about today. Now, if we go back to the question was an element that has 2 valence electrons, and that 2 valence electrons should be in group 2. And one of those fits. And it's not going to be S. Everything in group 2 would be S2, right? All right, so that was good. I wanted to add that to the one periodic table. All right, anything else on this quiz? Okay, so this is Sunday, right? Sunday for the quiz, and then I'll hopefully, I haven't looked lately, but hopefully you guys have got quite a bit of that rolling. So I can put this to the side, and then we just got started a little bit here. And this is all about metallic bonding, covalent bonding, and ionic bonding. And we are going to actually draw out some loose structures today. We're going to have enough time to get to that. I want to show you a video that's really good on metallic bonding because we don't cover much of metallic bonding at all. All right, please, please, please do not go on your cell phone. I went to a guest speaker the other day and A couple of people talked about the Vietnam Air and Kent State University where they're at, where people got gunned down and a student was on his cell phone. I want to just.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 21. It's on metallic bonding. And it's important that you understand that you can't have one metallic bond. You have to have a number of atoms together sharing their electrons and therefore sharing their bonding. And so the way we look at metallic bonding is the electron C model, where you have all of these electrons and they're shared by all the atoms. It creates a sea of electrons, and then the protons are kind of held on the inside of that. And so in metallic bonding, what we have are delocalized electrons, or electrons that have a freedom to move. And the way we visualize that is through this electron C model. It accounts for a lot of the properties of metals, like their conductivity, malleability, ductility, low volatility. And sometimes we have to go to the shell model, however, to explain new phenomena, and we'll get to that when we're looking at melting point. And all of that has to do with bonding. And so if we look at metallic bonding, or these shared bonds between all the metals, visualize it like this. We have the positive charges of the protons in the nucleus, and then we have electrons that are free to go. They don't want to get too close to each other. They're going to repel each other. And so what they do is they simply drift around, and they're constantly in motion. And what you create is this sea of electrons that have a negative charge, and then the protons are going to be held on the inside of it. And that's the best way to visualize the metallic bonding. And remember, these are going to be transition metals. So these are going to be atoms that have a lot of unpaired electrons in their d orbital. And as a result, these electrons have freedom to move. And as a result, we have all of these properties that come from metals. So number one, they're very good at conductivity. So that means conducting electricity and also conducting heat. And the reason why is that electricity, for example, is simply the flow of electrons. And so if we have free electrons, it's easy for them to flow through that metal. Likewise with heat, since those electrons and those atoms have a huge amount of freedom, we can move a lot of that energy through the material. They also are incredibly malleable. And what malleable means is that you can hit them and they're going to flatten out. So if you're a blacksmith, you're using that property of heating up these atoms in the metallic bonds. And then as you hit it, you're able to slide them past one another. It's going to be smooth sliding. And that explains how we can get something like gold leaf, which is simple gold that we hit over and over and over again until it's razor thin. They also show ductility. And what ductility means is it's ductile, or that means that if we pull it, it's going to stretch rather than break. And so if we were to test the tensile strength of different materials, so what you do is you put them in a big vise like this, and then you simply pull on it. If something's ductile, what that means is as you pull on it, it's going to stretch out before it eventually breaks. If it's not, it's brittle, what it's going to do is simply break in half. And metals show this. And the reason they show that is that all of these atoms have freedom to move around each other. And so when you pull on it, it's going to stretch it out. They also show low volatility. What that means is that they're going to have a high melting point and a high boiling point. Why is that? Well, think of all the positive charges we have down in these metals. We have all these negative charges, and so there's going to be a huge attraction between the two. And so it's hard to pull off individual ones to make them a liquid or eventually to make a gas. And so you would think as we move across the transition metals, so let's say we're going across this period from scandium to zinc, as we move across, we should be increasing the number of electrons. And so we should be increasing something like this, melting point. It's not really right. And so let's look at what the data looks like. So as we move across the period, it starts to go up for a while, but then it dips, and then it eventually goes down quite a bit. And so this whole idea of an electron C model works well, but when you get to something like this, we have to start digging into the shell model to make sense of it. And so let's start by looking at some electron configurations. So if we're looking at scandium, it's going to have 2 electrons in its 4s, and that's something interesting about transition metals. Their valence electrons are actually going to be at a higher level, but inside the s subshell. Anyway, as we move across, what we're doing is we're increasing the number of electrons. So we're increasing the number of valence electrons. And so as we go to titanium, and then as we go to vanadium, this all makes sense. If you can increase more of these electrons, increase more of that charge, it's going to be harder to get this thing to melt. But if you look here, when you get to chromium, it kind of dips. And the reason why is that it actually is not going to fill this 4s. before it jumps into the 3D. And then as we go to magnesium, you get a real stable shell structure where all of these are filled, and so the melting point is going to drop off. But now that pattern picks up again. Okay, now we're going to start adding electrons. So when you go to iron and to cobalt and to nickel, now we're adding these paired electrons. And as we pair those electrons, now we don't have those free electrons anymore. And so we're going to decrease the melting point as we get all the way down to zinc. And remember, as we get to zinc, we're moving over towards those nonmetals. And so we're starting to see odd properties as well. And so metallic bonding is pretty simple. Did you learn to use a delocalized electron models to predict macroscopic properties of metals? If you understand the C model and you see how it affects conductivity, malleability, ductility, and low volatility, then you got it. And I hope that was helpful.
So I've got my essay written, and I've been working.
By the way, if you are a biology person or something like that, he just goes by Mr. Anderson, Bozeman Science Teacher of the Year, which I'm assuming is Bozeman, Montana. His specialty really probably is more life science stuff. But that's, if you look at, he's got some great videos, absolutely fantastic videos. They're done very well. Okay, let's look at, let's carry on where we're at then. Okay, so we are going to, these chapters look at bonding, not much metallic. We just talked about metallic. I let Mr. Anderson talk about metallic with a sea of electrons. Otherwise, covalent bonding involves a sharing of electrons. And from each atom's outermost shell, or we are always talking about valence electrons. In most chemical compounds, the electrons are shared unequally between atoms, with the extent of sharing varying widely from very little sharing, mostly ionic, to considerably sharing, mostly covalent. So what's the big difference between ionic and covalent? Covalent has a lot of sharing of electrons, and ionic does not. Okay, so that just kind of introduces stuff in section 8.1 of the text. If we go to 8.2, it says, we're talking about covalent bonding and Lewis structures in molecules or polyatomic ions. Now, what do we mean by polyatomic ions? You know, we've got nitrates, phosphate, perhaps. We are talking about this is the key. We're talking about non-metal atoms here, non-metal atoms. The atoms are attached by covalent bonds. So if you have non-metal atoms, you're really talking about covalent bonds. And an example of that as a compound, simply carbon dioxide, carbon monoxide, water. I'm just writing down some compounds, NH3. I'm just writing down some compounds that are just put together with nonmetals, right? Covalent bonded nonmetals. Okay, core versus valence electrons. For group A elements, that's groups 1, 2, 13 through 18 as described in the textbook, but we're going to look at our periodic table on that. The valence electrons can easily be predicted from the periodic table. Core electrons are not involved in bonding. So that's what we just looked at. Everybody, I believe, has this table, and I'm just using this one because it's a larger version, I believe, of the one that I handed out. I'm going to double check it. Yeah, see, here's the problem. It's very frustrating. So for whatever reason, my table has 3A here. This table I handed out to you has 3B. The textbook, I don't know if they have A or B, I don't know. So to avoid all that, we just use group numbers 1 through 18, right? 1 through 18 avoids all of that. But realize if you're doing some questions in OWL, I don't have the book with me, they might reference, I'll probably see it coming up, they might reference 4B. And it might be this column, but double check. Once you see a question pop up with OWL, double check how this periodic table that you have matches up. Now, I always put the group numbers in parentheses, so like if it's an OWL question and it says like 3B, I would just put down like 13. So we know that the group number tells us the valence electrons then, right? Everything group 1, 1 valence electron, group 2, 2 valence electrons. Group 3 through 12, we got all kinds of d orbitals filling. And then group 13, 3 valence electrons, 4 valence electrons, 5, 6, 7, and 8. Helium only has 2 valence electrons, right? Helium. Okay. So now we'll get to the main thing we need to do, which is Lewis structures. So American chemist Gilbert Lewis, 1875 to 1946, introduces a system in which the symbol represents the nucleus and core electrons. And valence electrons are the dots. So valence electrons are the dots. So let's go to the next page here. So Lewis structure, Lewis symbols of elements, basic rules. Draw the atomic symbol. This represents the atomic nucleus along with the core electrons. What are the core electrons? Just the ones that aren't valence electrons. They're the closer ones to the nucleus. So we do the electron configuration notation of calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Well, the core electrons are what I have in yellow here. Right? Those are the non-valence electrons. So when you write down this symbol here, whatever element it is, I represent it as X, equals the core electrons and the atomic nucleus, and we know what's in the nucleus is protons plus neutrons, right? Then you'll see a box. You see 4 boxes around the element. Treat each side as a box that can hold up to 2 electrons. Count the electrons in the valence shell. Start filling boxes. Don't make pairs unless you need to. So if I did this with 2 valence electrons, I would typically, we start on the right and go, it doesn't really matter. We put 1 dot here. I'm going to go counterclockwise. I'm going to put 1 dot here. It doesn't matter. We have 2 valence electrons, 1, 1. So now here's table 8.1, Lewis electron dot symbols for the main group atoms. So let me zoom this in. So this is group 1, and we know that if we did this, this is group 1. This is group 2, group 3. This would be actually 13. This is group 14. 15, 16, 17, going across and 18. Remember, this N would just be our level, right? Sorry. And we know the ones place, I should do it this way. We know the ones place is going to equal our valence electrons, right? The ones place is going to equal our valence electrons. Okay. I'm going to do this problem. It seems like I'll put some homework out there that it's just asking you questions about Lewis structures you haven't driven. You haven't written one yet. We're going to do this question, then we're going to draw some Lewis structures. So we know that except hydrogen wants 2 electrons shared. And then pretty much everybody else wants 8 valence electrons. And that is a stable octet. So let's look at this question here. So we know that this, just a solid line, represents a bond of 2 electrons. So one of those would be from hydrogen, one from carbon. In fact, how many valence electrons does carbon have? 4. And then you look at how these are shared. So I'm going to draw some dashed lines. And I'm not going to do the hydrogens, but that hydrogen has 2 electrons. Perfect. This hydrogen has 2 electrons. Perfect. I'm going to draw a dashed line like this. How many electrons does that oxygen have around it total? 8, right? So that's perfect. That oxygen's happy. And if I draw my blue circle now, how many does carbon have around it total? 2, 4, 6, 8. Carbon has 8 too, correct? So this is a good structure. How many does chlorine have around it here? 8, that's good, right? That's good. How many does nitrogen have around it if we draw it out like this? Two, 4, 6, 8. That's a good one. Let's go to the one below it. It's the one below it is junk. First of all, how many electrons are around oxygen here total? 2, 4, 6, 8, 10 electrons, right? So this is junk already. That's 10 electrons. And this nitrogen here in the middle, maybe I should start using a highlighter. 5 pairs of 2. This is 10 electrons. This is junk. Let me try highlighter. So here's 2, 4. There's 8 for that oxygen. That's all good. 8 for that oxygen. There is 2, 4, 6, 8 for that oxygen. That's good. This oxygen here, 2, 4, 6, 8. That's good. That oxygen's happy. And then this middle nitrogen has, there's 4 here. 2, 4. Everything looks good on that one. Everything looks good. All right. It's time then to draw a Lewis structure. So I have it into this worksheet. There's directions and there's a worksheet on Lewis structures. So I'm going to flip back and forth. And the worksheet's actually at the very end in the directions. So we have something that looks like this. Directions for drawing Lewis structures about the 5th to the end. So we'll get one of these drawn out here a little bit. Okay. So I'm going to follow these directions number by number by number by number. Okay. And typically we're doing covalent bonds here. Covalent bonds. So it says, write the skeletal structure, the arrangement of atoms within the molecule. The central atom is a lone atom or the atom with the lowest electronegativity, usually written first. Well, hydrogen's always turned on. We're just going to do one. So we have enough time to do it. So on the worksheet, the very next page, get an idea. We're going to do CH4. So let's do this one here. We want the total valence electrons. So total valence electrons. So carbon has how many valence electrons? What group number is carbon in? Carbon's in group 14, right? So carbon has 4 valence electrons. For hydrogen, there's 4 hydrogens at 1 each. So if we add all these up, 4 for the carbon, 4 hydrogens at 1 each. My total valence electrons is 8. Okay, so I want to make sure that I'm following these directions. So count the total valence electrons. The group number for each element equals the valence electrons. We talked about that. Add electrons for negatively charged ions such as NO3 minus. Subtract electrons for positively charged ions. Okay, so we counted the valence electrons. It says draw a bond between the central atom and each surrounding atom. A single bond is just 1 pair of electrons. So my central atom is going to be carbon. Hydrogen's always a terminal on the outside. So I'm going to put carbon here. in the middle. And then I'm gonna put hydrogen, 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 hydrogen on the outside. I kind of made this crooked, but we need a pair of electrons to make a bond. So this is our electron structure for CH4 if at this point everybody's happy. First of all, what is my total number of electrons I have here in my Lewis dot structure? My total number of electrons is 8, right? I've got 8. How many valence electrons do I need? 8. Hydrogen for a stable octet needs 2 electrons, right? So hydrogen is happy with 2, right? That hydrogen, this hydrogen, this hydrogen, this, right there, everybody's happy. Okay. I put this in the middle because I know there's not going to be multiple bonds resonance structures until we get down farther. Now, from OWL, I think this comes out of OWL or maybe the book. The electron pair geometry is the geometry assumed by all the valence electron pairs around a central atom, carbon in this case, both bond and lone pairs. This is different than the molecular geometry. So the electron pair geometry is these electrons, there are 4 sides to it, if you will. And I'll save the next one for later because this doesn't show the difference. Now, here's where things. Here is where this blue sheet becomes the savior sheet. So on this blue sheet, this is the central atom. I use this uses the terms bonding domains, non-bonding domains. And for bonding domains, it's how many bonds are on the central atom. And it doesn't matter if it's single, double, or triple bonds. It equals 1 bonding domain. And then the non-bonding domains are pairs of non-bonded electrons. So I'll just use a couple examples because I got them right here. The first one says it's a 2-0. Bonding domains is 2, non-bonding domains is 0. If we go to the right, this is for carbon dioxide. On the central atom, there's a double bond on each side, right? It doesn't matter if it's a single, double, or triple bond. It is 1 bonding domain. And on that central carbon atom, there is 0 pairs that are non-bonded to terminal atoms, correct? This is a 2-0. If I go to this one down here, How many bonding domains do I have there on the central atom of nitrogen? This would be 3. The double bond on top is 1 bonding domain, single bond, single bond. This would be called a 3-0. There is no pairs on the central atom that are not bonded. When I go to this one right here, oops, this one right here. This is a 2-1, 2 bonding domains. Single bond, single bond. There is my pair of electrons that is not bonded. Here is our CH4 that we just did. This would be a 1, 2, 3, 4 bonding domains and 0 non-bonding domains. This is a 4-0. If we look at this one, there's 1, 2, 3 bonding domains and 1 non-bonding domain. We would call this a 3-1. Here's water. How many bonding domains? 2. How many non-bonding pairs? 2. This would be called a 2-2. So for our example that we just did, this is a 4-0. All right, there is our first Lewis structure. There is a take-home quiz, I believe, that's already loaded. You can only do 1 through 3 so far. Just to get to it. There should be a 8 and 9 take-home quiz out there. Of course, it's our last one, right? All righty, everybody have a great weekend. And we'll see you on Monday.